Okay, so the first thing we're going to look at in C5 is the different reactions between metals and compounds. But first, there's a few key terms I want to define. A base is any substance with a pH greater than 7, so that would include metal hydroxides and metal oxides. An alkali is simply a base that dissolves in water, so that would include metal hydroxides. And an acid is any substance with a pH below 7. And at GCSE level, you need to know the formulas for 3 acids: hydrochloric acid, which is HCl, sulfuric acid, which is H2SO4, and nitric acid, which is HNO3. And then there's the equations themselves that we need to know. So number 1 is that when you mix a metal and an acid, you will form salt and hydrogen. But when you mix a metal oxide with an acid, you've introduced oxygens, so we're now going to make salt and water. If you mix metal hydroxide with an acid, you will also make salt and water. But if you mix a metal carbonate with an acid, you've now introduced carbon as well as oxygen. We're going to make salt, water, and carbon dioxide. So building on from this, the name of the salt made depends on the acid used. So if we use hydrochloric acid, we're going to make a metal chloride. If we use sulfuric acid, we'll make a metal sulfate. And if we use nitric acid, we'll make a metal nitrate. For example, potassium nitrate. And you can test for the products of the previous reactions. So to test for CO2, you bubble the gas through lime water. If CO2 is present, it will turn cloudy. Alternatively, a lit splint will go out. To test for hydrogen, obviously the solution will fizz, but also if you place a splint in a test tube full of hydrogen, a squeaky pop will be released. And to test for oxygen, place a glowing splint into a test tube of the gas, and that should relight if oxygen is present. It is really common to get a 6 marker on making crystals, so it's really important you learn this method to write in your exam. The example I'm going to show you is making copper sulfate crystals. So if we're told to make copper sulfate crystals, we know we've got to use copper, so copper oxide, copper hydroxide, copper carbonate, and we're going to need sulfuric acid. So I'm going to choose copper oxide. So step number 1, we add copper oxide to warm sulfuric acid and stir. Continue adding the copper oxide until it is in excess. Filter the contents of the beaker using a funnel and filter paper over a conical flask. Make sure that you're including the equipment. When filtration is complete, pour the contents of the flask into an evaporation dish. Evaporate this gently using a Bunsen burner and a water bath, because a water bath gives a gentler way of heating, on a tripod and gauze. Stop heating once at boiling point and leave to cool for 24 hours, then dry the crystals with a paper towel. If they ask you to make neutralization crystals, you'd add a metal oxide, hydroxide carbonate, to an acid, but you'd add that with universal indicator added. And we can see how much acid is needed to react completely, so until that UI will turn green when it's neutral. You then add that same volume of acid again to the alkali, but without the indicator added. Crystallize those crystals using the method we've just discussed, but don't bother drying them, okay? The next topic is the reactivity series, which lists how easily metals can form their positive ions. You will need to learn this, so I use a quick rule to help me remember the first letter of each of the metals, and that is: please send lions, cats, monkeys and cute zebras into hot countries, signed Gordon. Potassium, sodium, lithium, calcium, magnesium, aluminium, carbon, zinc, iron, tin, lead, hydrogen, copper, silver, gold. Now, although carbon and hydrogen aren't metals themselves, they're included as references to compare. They may include here alkali metals and their reactions with water. So remember that they will fizz, producing hydrogen gas and leaving behind an alkaline solution of metal hydroxide. But our top 3, potassium, sodium and lithium, will explode when they are reacting with dilute acid. And the relevant experiments to identify the reactivity series may also crop up here. What you do is measure the temperature change throughout the experiment. More reactive metals will produce more heat, thus will have a higher temperature change. And your control variables here are to control the same mass, surface area, and type and concentration of acid. And just a quick note here that reactions with water are slow. That makes it difficult to order, which is why we react the metals with acids as well. And then we have oxidation and reduction or redox reactions. Now, most metals come from ores. Ores are compounds in which it is economically viable to extract metals. A metal ore is also called a metal oxide, so that would be formed by reacting metal with oxygen, and that metal oxide would actually tarnish the shine of a metal. Now, we have the acronym OIL-RIG. Oxidation is the loss of electrons, reduction is the gain of electrons, which we'll use later on. And just a quick note that metal plus water makes metal hydroxide and hydrogen gas, and in the cases of alkali metals, this is an explosive reaction. The next topic is displacement reactions. This is where a more reactive element displaces a less reactive element. For example, magnesium is more reactive than copper, so it will displace it. Copper sulfate plus magnesium makes magnesium sulfate plus copper. Magnesium is more reactive, so it kicks the copper out of its compound and displaces it, so it's left by itself. If a more reactive element is already in a compound, it won't react, and this whole principle can be used to extract metals from compounds in a process that we call smelting. Carbon is more reactive than most metals, so it is often used for the extraction process, which is done in a blast furnace, hence its name smelting. However, it's important that we recognise that not all rocks are known as ores. Some have such a small percentage of metal in them that there isn't enough economical gain in extracting them, and that would depend on how easy it is to extract them, as well as how much metal there is and the changing demands for that metal. Not all metals are extracted using carbon, however. The exception is tungsten, which is extracted using hydrogen, because otherwise it would form the compound tungsten carbide. Instead, the tungsten obtained is obtained very pure. The metals need to be concentrated before they are extracted and purified. Metals are ground into a powder and water is added, as well as chemicals that repel that water. Air is then bubbled through the mixture and the compound floats to the surface as a froth that can be scraped off and obtained. Half equations. Half equations show the movement of electrons. So, for example, if calcium is displacing iron, we have the reaction Ca plus Fe2 plus makes Ca2 plus Fe. Now we can see that calcium is becoming ionised, Ca making Ca2 plus, but we need to balance out those charges. On the right hand side of the equation, Ca2 plus, there is 2 more protons than there is electrons. To balance out those charges to make the neutron or atom that we had before, we need to add 2 electrons. Now we could actually write this as Ca take 2 electrons makes Ca2 plus, but we can also write it as Ca makes Ca2 plus 2 electrons, and this is oxidation, it's the loss of electrons. The reduction is a little easier, so iron Fe2 plus makes Fe. Now we need to balance out those charges. We've got 2 more protons than electrons on the left hand side, so we need to add 2 electrons, so we are gaining electrons, so that is reduction. The harder equation that might pop up is the oxygen one. We need to make sure that we know that halogens, as well as oxygen, nitrogen and hydrogen, are diatomic molecules. They come in 2. So if we had oxygen, O2 minus, that's got to make O2. So we need to balance this equation, so we're going to add a big 2 in front of the O2 minus. Now that means that we've got actually essentially O4 minus making O2, so we need to add 4 electrons onto the product side, which would be oxidation. The key thing for neutralisation is the pH scale, and you need to know that neutral pH is pH 7, and that will be green in UI. And when we go down the pH scale from 7 to 0, we're going to be looking at yellow, orange, and then red at the very acidic end, so 0, 1, 2 sort of area. The other side, so 7 to 14, we go blue, and eventually when we hit 12, 13, 14, we're going to be looking at purple there in UI. All acids have hydrogen ions, all alkalis have hydroxide ions, and when an acid is reacting with an alkali, a neutralisation reaction occurs, and the equation for neutralisation is acid plus alkali or base makes salt and water. So, in other words, H plus OH minus makes H2O, which is neutral with a pH of 7. For neutralisation, you must have exactly the same ratio of acid and alkali, and a pH probe provides a more accurate reading for pH than UI. This can be hooked up to a data logger to view continuous data. The pH scale is also a logarithmic scale. This means that as the pH increases by 1, the concentration of H plus ions decreases by a factor of 10. The method for the pH curve experiment is to measure out 25 centimetres cubed of sodium hydroxide and place it in a beaker, measure the pH and add 5 centimetres cubed of hydrochloric acid and repeat until a total of 50 centimetres cubed have been added, and make sure that your line of best fit on your graph is a curve. Just a few notes here that the more hydrogen ions in a solution, the more acidic that solution is. Acids are corrosive, dilute acids are cheaper, and we dilute acids by using distilled water. Now, from a strong acid to a weak acid, strong acids are corrosive, then they become an irritant, then when you approach a weak acid, they are harmless. Now, concentration is a measure of the number of particles of a substance in the water. A concentrated acid means that there is a large amount of acid particles relative to the water particles. A dilute acid means there is a small amount of acid particles relative to the water particles. Strong and weak acids are something completely different. Strong acids will have a pH of 1 or 2. Weak acids will have a pH of 3, 4, 5 or 6. Remember, they're all before 7 because they're acidic. And we can test different acids to determine how reactive they are at 1 mole per decimetre cube concentration, controlling the concentration of the acid. We add magnesium into test tubes of 5 centimetres cubed of hydrochloric acid and 5 centimetres cubed of ethanoic acid, and we time how long it takes for the magnesium to disappear. It will take less time for the magnesium to disappear in the test tube full of hydrochloric acid, and this is because hydrochloric acid is a stronger acid. It also fizzes more vigorously, gives off hydrogen gas, and warms up quite a lot in the hydrochloric test tube. So what actually is a strong or weak acid? Well, the strength of an acid depends on how much the ions separate in water. So for example, hydrochloric acid. Hydrochloric acid is a strong acid, so it fully ionizes into H+ ions and Cl- ions. This is a reversible reaction, and that means it will eventually reach equilibrium. In a strong acid, all of the acid molecules ionize and become ions. Therefore, a high concentration of H+ ions means that this is a very reactive acid, and examples include hydrochloric acid, sulfuric acid, and nitric acid. In a weak acid, only a few of the acid molecules ionize and become ions, with the majority staying as acid molecules. Therefore, we have a lower concentration of H+ ions, and that means that we have less reactive acids. For example, ethanoic acid and citric acid. Just some final notes then. A salt is an ionic compound with a metal and a non-metal part. Metals that are less reactive than carbon are extracted using a displacement reaction in a blast furnace. But metals that are more reactive than carbon use electrolysis, which is the next chapter. Gold is special though, it's unreactive, it's found in the ground, not as an ore, it's a native metal. And that's the end of C5, so well done if you made it to the end of the video, and see you next time.